Welcome, this is Recitation 3 with the topic of infinite limits and vertical asymptotes. This is going to consist of problem solving. No new theory here, but lots of important techniques about how to solve these problems. I first have two examples that I originally planned for the lecture, but I didn't have much time there. So these will be quick and they will serve to remind us about what we are talking about here. So here we have a function which is cotangent, inverse of tangent, so that means cosine over sine. And we're talking about limits at 0. Talking about the lateral limits or one-sided limits and asking if they exist. So what happens in here? Let's say you were studying limit as x approaches 0 from the left of cosine x over sine x. Let's say you don't even remember what the topic of today is. You don't know this is going to be an infinite limit. So how do you analyze this limit? You simply start by trying to plug in 0, and you will see what happens. Cosine of 0 is 1. We need to remember those values, and then sine of 0 is 0. So this is of the form something not 0 divided by 0. So it is going to give you an infinite limit, and you need to understand the sign, remember? And that's going to be crucial here. So 1 is a positive number, different from 0, as we mentioned. And the 0 downstairs, we just have to understand if it's through negative numbers or positive numbers. And so now we have to remember that this limit is from the left. If you are to the left of 0, close to 0, sine is actually negative. Just think of the graph of the sine function, for example, as a way to understand this. You know, the graph of sine looks more or less like this. So if you have an x that's on the left side of 0, but close to it, sine of x will be negative. So what we have downstairs here is a negative number close to 0. So positive over negative is going to give you a negative. And now the fact that it's 0 downstairs but not upstairs gives you infinity. So that is this limit. And what's going to change when you do it from the right is the sign of sine. Sign of sine. Because cosine of 0 is still 1, sine of 0 is still 0. But now you're coming from the right side. Positive number different from 0 divided by positive number close to 0. And that's a plus infinity, because now it's positive over positive. And the answer to the last question where they asked, what about the regular limit? Does it exist? The answer is no. Because the two lateral limits were different. So that's what happens to the cotangent function around 0. And the other example that was in lecture, it's more of a conceptual type. This is just to remind us, you know, that when there's a 0 in the denominator, what happens is potentially there will be an infinite limit, but it's not always. So this is what this is saying here. If you have an f of x of the form g over h, in case the limit of h is 0, it's not always necessarily true that the limit of f will be infinite. This question is now telling us, find an example of this in this particular form. So in other words, find a possible function that you can put downstairs here that will be your h that goes to 0, but such that this limit is not an infinite limit. And what you can possibly think of in here is, let me pause to give you time to think. If you pause the video, you have more time. Just a function x. We should all know that sine x over x as x goes to 0 has a finite limit 1. Even though x is going to 0, what happens is that sine x is also going to 0. And when you have 0 over 0, you don't necessarily have an infinity. Your limit could be anything, or even it might not exist. So just because you see a 0 downstairs doesn't mean you have an infinite limit. You also, going back to the previous example, you also need to analyze what happens in the numerator. If that is not going to 0, then yes, you're going to have an infinite limit. So now we'll have about 7 problems, I believe. I'll see how many I can do in about 40 minutes. The other ones that I can't will be just left on the screen. So first of all, this remark here in all questions today, analyze the limit means find the lateral limits and conclude that the regular limits exist or not. That's what the word analyze means in here. And they will all be cases of infinite limits. So let's look at this first one. It's almost the same function between a and b. It's the same point, 3, but what's changing in these limits is the power. This is a cube, this is a square. You're going to see what changes here. So a, what happens as you come towards 3? Let's say from the positive sign this time. I think it would be easier to start with the positive instead of negative. So from the right. First of all, you try to plug in 3. 1 minus 2 times 3 is a minus 5. And downstairs, of course, it gives you a 0, 3 minus 3. So, okay, it is non-zero divided by 0. It's going to be infinite limit. So negative number different from 0 divided by, and here's the question, what is this number downstairs, positive or negative? Well, if you are coming from the right side of 3, this is where your x is, then x minus 3 is positive, which means x minus 3 cubed is also positive. So this number downstairs is a positive number. And it's approaching 0. You can say it's small, close to 0, whatever here. Just something to indicate that this is the reason why this is an infinite limit. And what is negative over positive? That's always negative. Cool. And from the left, here's the whole point for this problem. Again, the numerator is just minus 5. The denominator is 0. Numerator is negative number different from 0. But what's happening in the denominator now? Because you're coming from the left, x is before 3. Well, if x is less than 3, when you subtract 3 from x, that's going to be negative. And what is the cube of a negative number? That's also negative. So the denominator this time is negative. Negative number, small. Which means negative over negative is now plus infinity. And just to conclude, we found 2 different values, so the limit does not exist. Now let's contrast this to what's going to happen to item B, which I'm going to scroll up so we can see. The only difference, as I said, is this power 2 now. For B, one minus 2x, x minus 3 square. I'm just going to write minus infinity similar as above. The analysis is exactly the same, negative in the top, and because of the square downstairs, the way that this denominator goes to 0 is through positive numbers. And then negative over positive gives you negative. So this is okay. And now this other limit from the left is where things change. Because again, this is gonna be negative 5 over 0, which is a negative number, different from 0. But the denominator is still positive. Positive number and going to 0. Why is it positive? Again, we've seen an example in class, in lecture, because of the even power. The square here makes sure that it doesn't matter if you're approaching 3 from the left or from the right now, this is always going to be positive. Whereas in the previous example, it mattered because that was an odd power. So this time, it's still negative over positive, it's still negative infinity. And you see that the two one-sided limits are equal now, meaning that the regular limit is also whatever they were, which is minus infinity. This time it exists. So be very careful when you have powers in the denominator. You need to be paying attention to whether they are even or odd. And we're going to see that the next example has this as well. Here is the next example. Analyze the following limits. Let's look at the first one. So you see an even power there in the denominator. Maybe you're thinking, based on the previous example, that this means the limit is going to exist because the sign will be the same, whether you're approaching from one side or the other. The denominator will be positive. But you have to be careful now. What happens if you try to plug in -2? That should always be your first attempt. No matter what limit problem you're doing, try to plug in because maybe it's possible. But you see that what happens upstairs will also be a 0. This is actually a limit of 0 over 0, indeterminate form. That means it could be anything. We don't even know so far if it's actually going to be an infinite limit. What we have to do to understand is simplify. And simplification here is an easy matter. The easiest type of function that you can find to simplify is functions with a polynomial over polynomial. How do we simplify this? We factor. Try to factor this quadratic in the numerator. So you're looking for two numbers as the sum of 1 and a product of -2. That's going to be 2 and -1. And what's happening is you're actually going to cancel one of the powers of x plus 2. So the function that we have was disguised. It was actually this simpler function right here, where the power in the denominator this time is odd and not even. So we can now try to understand what happens to these limits. So limit as approaching 2 from the left. 2 minus 1 upstairs is just 1. Sorry, this was not a 2, it was a -2. My bad. -2 from the left. So let's try this again. Numerator -2 minus 1 is -3. And we are divided by 0. Okay, so now we can see this is going to give you an infinite limit. And what is the sign? Okay, so negative number, different from 0, divided by, well, if you're coming towards -2 from the left, -2 and then x here, x is more negative than -2. If you add 2 to that, x plus 2 is still going to be negative. Just think of it this way, because x is less than -2, and the number that you're trying to understand is x plus 2. This is going to be less than -2 plus 2. So I am simply replacing this x with -2 with the less sign, which was given above. And -2 plus 2 is 0. So x plus 2 is negative in this case. Negative number, small, approaching 0. Negative over negative is positive. Meanwhile, approaching from the other side, will actually give you a different sign in the denominator. Just think about it the same way. Let's see, x is larger than -2 now. So if you do x plus 2, you fall on the right side of 0. You fall on the positive numbers. And negative over positive is minus. So the limit at 2, let me write f of x for simplicity, does not exist. All right, this was item A. B is a similar one, just different functions and different number. So let's see that. X squared minus 4x plus 3 divided by x squared minus 1 x minus 5. Yes. So once again, first thing that you should try when you see a limit, plug in 1 to see what happens. And you will quickly realize this is 0 over 0. Indeterminate. Which means we need to simplify it somehow. And it's the same trick. It's a polynomial over polynomial. Usually when you try to simplify it, at least one of the factors that appears downstairs will also appear upstairs. That's how the simplification takes place. In this case, x minus 1 times x minus 3 gives you the numerator. And in the denominator, let's try to completely factor it. You have an x squared minus 1 here. We should all know that this is equal to x minus 1 times x plus 1. It's that famous expression, a plus b, a minus b, gives you a squared minus b squared. And now you can see there is one factor in common. And it's precisely a factor that we can cancel because, well, you're going towards 1. That means x minus 1 is never 0. It's just close to 0, so you cancel those. And what happens to this limit now? Turns out you don't actually need to evaluate the lateral limits separately here because there is no problem here. It's not going to give you different answers. You can just plug in this time. 1 minus 3 divided by 1 plus 1, 1 minus 5. That's a perfectly well-defined number. 2 times minus 4. So minus 2 divided by minus 8, it's plus 1/4. This is not an infinite limit, actually, even though it might have looked like one. So those were the questions about simplification. Next ones, again, something will change between these two, which are very similar. We have square roots now. Analyze the following limits. Let's look at A. Obviously, plugging in x equals 1 will give you 1 over 0. So you know this is non-zero number divided by 0. This is going to be infinite limit. And we will have to understand the two sides because of this square root function. So let me try to analyze what happens coming from the right. Okay, so as I said, as you come towards 1, the denominator becomes 0. And the numerator is just 1, so this is positive number, which is non-zero, divided by a number that is going to be very small, but what is the sign of that number? Okay, so you have to realize if x is larger than 1, then x minus 1 is positive, which means you can take the square root. It is well defined, and a square root is always positive. By convention, the symbol square root of anything, as long as that thing is not negative, is positive. And if you want the negative square root of that number, then you have to put a minus sign in front. So this denominator is a positive number that's small and going to 0. So positive over positive is positive. This is a plus infinity. Meanwhile, what's happening from the other side? The answer is nothing is happening. You can simply write D and E here. This does not exist because the reason, can you see it? The the function is undefined when x is less than 1, which is the case here. If you're coming towards 1 from the left side, then x minus 1 is negative, and you cannot take a square root of a negative number when you're working with real numbers. So yeah, this limit cannot be taken from the left. You're coming from a place where the domain of the function doesn't even exist. So you actually only have a right limit for this function. And you do not have a regular limit because one of the one-sided limits did not exist. All right, so what does this all mean, by the way, for the graph of this function is that around the number 1, here's the number 1. The function was becoming very big, was growing towards infinity on the right side. Meanwhile, on the left side, it doesn't even exist. There is no graph on this region before 1, or at the number 1 either. Now, this limit behavior doesn't tell you much about anything else. Like what does the graph do after this point? It turns out it just goes towards 0 like this. But if you're studying a limit at 1, then that's going to give you information about only close to 1. But I'm just saying this so we connect this to actually graphing and no vertical asymptotes. This line is a vertical asymptote to the graph. Item B now is the same, almost the same, but the number inside of the square root is squared. So you have x minus 1 squared now. And that's going to make a big difference here. What happens here? Well, please do not say this. You should always remember this, by the way. The square root of a number squared is actually not always equal to that number. In general, for example, the square root of minus 3 squared is not minus 3. It's not the number. It's not like the square root and the square cancel. It's actually plus 3. So in general, the square root of a number squared is the absolute value of that number. That's what's true. In other words, when you square first, you're making the number positive, and then we take the square root, that becomes also positive. So you can use that in this problem. You actually can say that the square root of the square is just the absolute value. And when you look at this, you realize this is a case where you need to analyze the two separate. I mean, you don't need to analyze them, but we will, the two separate one-sided limits. But as you can see, both will give you a positive value because there's a absolute value in the denominator anyway. So you can simply say this limit is equal to 1 over positive. So it's a positive number that is non-zero divided by a positive number that's very small. So, okay, I did not actually analyze the two lateral limits separately. I just concluded that whatever side you're coming towards 1, this denominator, because it has an absolute value there, will always be positive. And also the numerator, of course, is always positive. It doesn't depend on x. So this will give you a plus infinity. And in particular, also the one-sided limits are plus infinity. Okay, so what changed here comparing to the previous item is now that this function is actually well-defined before the number 1 as well. I'm gonna draw its graph up here, just so we understand what's happening. For this function, there is also another leg, another piece in here. And it's just not defined at 1, but you see that both pieces are going towards infinity. Moving on. A few more limits to analyze. the same way. Now we have some trig functions in here. I wanted to pay attention especially to item C. There's a trick question there. So let's see. What you should be thinking about in A is that because this is all a bunch of trig functions, try to rewrite them using only sines and cosines and simplify as much as possible. I mean, that's at least after you have tried to plug in. But if you plug in theta equals 0 here, you'll see both cosine and secant of 0 are equal to 1. And then 1 minus 1 is 0. So there is a 0 in the denominator, but also a 0 in the numerator with the tangent. So you need to simplify somehow. And that's what I'm going to do. Tangent is sine over cosine. Then secant is 1 over cosine. And then cosine is just cosine. Let me try to find a common denominator in the denominator. This will be like 1 minus cosine square divided by cosine. Now you know that if you have a fraction of fractions, you can basically just multiply by the reciprocal of the fraction in the denominator. And you can cancel these cosines. So we have been able to simplify this all the way down to sine theta over 1 minus cosine theta squared. So there was a simplification already. We canceled cosines. Maybe now if we plug in, it will be possible to find a value. We should check that first. But actually, no. Theta equals 0 will give you a cosine value of 1 here, and then 1 minus 1 is 0. So you still need to do something here. And you probably already realize 1 minus cosine square is the same thing as sine square. Because of the fundamental identity, Pythagorean identity for sine square plus cosine square equals 1. And here you can cancel one factor of sine. So now you're in good shape. Plugging in theta equals 0 will give you 1 over 0. So you know it's going to be either plus or minus infinity. So it might actually depend on which side you're coming from. In this case, it does depend on that. Let's do that quickly. I'm just going to indicate this. If you're coming, for example, from the right, then sine theta is positive. Sine of a small number larger than 0 is positive. So this will be a plus infinity because sine theta is positive. Whereas if you're coming from the left, then sine theta is a negative number. Again, just think of the graph of the sine function. So we have two separate answers for one-sided limits. Meanwhile, the limit does not exist. Precisely because we had two separate values. That was item A. What does item B look like? This one, we can solve right here. We don't really need that much space. It might look complicated. We have an exponential and sine. Whenever something looks that complicated, it's probably going to be very easy. Try to plug in and see what happens. E to the 0 times 0 plus 2 divided by sine square of 0 plus 0 to the 4th. What is that? E to the 0 is 1. Do not think that this is a 0. That would give you some trouble. No, it is 1 times 2 upstairs. That's a 2. And downstairs we have a 0. So we know it's an infinite limit. We just have to understand the sign. And it turns out that it doesn't even matter which side you're coming from. What is the sign of this downstairs 0 here? It's positive. And we can say this is because, just look at the denominator function. you have a square and then also a fourth power. Those are always numbers which are larger than or equal to 0 for all t, actually. The square or even any even power, they're always positive or 0. So that's how we know the sign of the denominator. Don't even need to analyze lateral limits. So that was a very easy example. And C is a trick question. Sine x over x squared. I mean, it's not a trick question. You at least realize that you cannot simply plug in. If you plug in 0, sine of 0 is 0. That's indeterminate. If you try to do it this way, you realize there is nothing you can do. So we have to do something to simplify this. Problem is there isn't much to do in terms of simplifications. One function is a trig function, the other is not. And the only limit that we really know involving these functions is sine x over x. So how about we use that? How about we rewrite this expression this way? Sine x over x, the whole thing over x. I mean, this is true. This is the same thing as the original function. But now it's in a form that's useful for us. The limit upstairs, again, upstairs, it's not like we can plug in 0, but it's a limit. And that limit is a 1. So maybe I'll put the limit first to indicate exactly what we are doing. It's not like the function upstairs has a limit. I mean, it's not like it has a value at x equals 0, but it has a limit as x equals 0, and that limit is 1. So now we recognize that this is a 1 over 0. This is of the form that gives you infinite limits. And you just need to understand the sign of the 0 here. Does it come towards 0 always with the same sign? Or is it positive from one side and negative from the other side? Well, the answer is the second one. The function is x in the denominator. If you're coming from the right, x is positive. If you're coming from the left, x is negative. And that's because you're coming towards 0. So you have to separate this out. From the right, it is going to be 1 over 0 equals plus infinity, because x in the denominator, this x right here, is positive. And maybe I do this. I'm going to copy all this. From the other side, it will be negative. So from the left, minus infinity, because now x is negative. Meaning, by the way, as usual, they are just asking us to analyze the functions. So this all means that the limit itself does not exist. That was this problem number 4. All right, now here is just a quick reminder. Let's now start talking about vertical asymptotes, which, as I told you, is secretly the same topic. But now the questions will mention vertical asymptotes. So one of the things that we learned is that a line x equals a is a vertical asymptote if and only if actually at least one of those is following the following limits is true. Either the left limit or the right limit or both at that number a should be plus or minus infinity. And this can only happen at points where the function is not defined, so outside of the domain, but bordering the domain at least, so that you can actually approach the number. So if you have a question like number 5, where they give you a function and say, find all the vertical asymptotes, if any, secretly, this is a question asking you, what are all the points where you can find an infinite limit? And you need to understand that, how to find those points. So they're not directly asking for a limit, but they're saying what are the points where you have an infinite limit. And the answer for a fraction like this is always the candidates for those points are going to be the point where the denominator is a 0. So that's how we're going to be solving these problems. For example, in A, try to first of all find the places where the denominator, x squared minus x minus 6, is 0. Well, if you factor this, minus 1, minus 6, so there's only 2 points, 3 and negative 2, where you can potentially have a vertical asymptote. That doesn't mean you necessarily have them in there, because you know that the numerator might also have some factor canceling them. But it's going to be at most these two. Now we need to analyze them separately, but we'll try to also simplify the function. I'm just going to write we need to find the limits at 3 and negative 2. Not only the limits, but actually also plus or minus here, one-sided limits. If one of these is infinity, that means there is an asymptote. And if they're not infinity, there is no asymptote there. Now, okay, let's take another look at the function and simplify it. Well, x squared minus 6 minus 9. Or sorry, it was plus 9. Plus 9. You may recognize the numerator as x minus 3 squared. So if you are going towards 3, for example, you can cancel the number x minus 3 because it's not 0. There is still going to be one factor left in the numerator, but no factors in the denominator. So the function is actually this simpler function here, except at the points 3 and negative 2 where it's not defined. But now you can understand that, for example, one of those two candidates that we just found, positive 3 and negative 2, the candidate positive 3 is actually no problem at all. If you plug in 3 here, you have 0 over 5. It's 0, no vertical asymptote. Because you did not find the value of infinity or minus infinity. However, at the number 2, negative 2, the other candidate, there will actually be a vertical asymptote. How much is this limit? Well, the limit itself does not exist. If you try to analyze the signs again, you will soon realize this x plus 2 is either positive or negative depending on which side you're coming from. So this limit does not exist. But remember, for a vertical asymptote, as long as at least one of the one-sided limits is infinity, that's already enough. So for example, we can add a little plus here, let's say. Let's say we just come from the right. That will already be enough for us. What's happening as you're coming towards negative 2 from the right? Okay, upstairs will be a negative 5. Downstairs will be a 0, but it will be the case that positive number. If x is larger than negative 2, then x plus 2 is larger than 0. So this is actually minus infinity with this negative upstairs. Minus infinity because x plus 2 is positive in this case. So because there was an infinity value there, this line x equals negative 2 is a vertical asymptote. And it's the only one. That's basically the same thing for item B. Maybe I'm going to skip that in here. Again, just talking about it very briefly. Find all the vertical asymptotes. Well, you want to understand what are the places where the denominator can be possibly 0, first of all. Those will be all of your candidates for asymptotes. So I'm going to just go ahead and factor this for you to help you get started. Upstairs, you know that you have x plus 1 times x minus 1. Downstairs, think of x to the fourth as x squared squared. So it factors as x squared plus 1, x squared minus 1. And then the x squared minus 1 also factors. So this is the function fully factored, and you see that after canceling, the function is actually equal to 1 over x squared plus 1, except at the numbers where you could not do this cancellation, which were minus 1 and plus 1. So those are the numbers where the asymptote could possibly happen, and you have to analyze the limits in there. But I'm going to leave this to you. I'm going to be solving item C here. This one. Square root of x squared plus 9x plus 20. The function is called h. Divided by absolute value of x plus 4. Okay. The problem is again the same. Where are the vertical asymptotes? Well, to understand that, you need to understand the places where you can possibly have undefined values for this function. That could be either when the denominator is 0, which means, well, if the absolute value of a number is 0, then that number is also 0. That's the only possible way to have that happen, because it's plus or minus 0. So x is minus 4 is a candidate. I think it's a good idea to label them as candidates. It doesn't mean that yet that they are going to be vertical asymptotes. You need to understand the limits. And then the other places where you can have problems here is if the function inside of the square root becomes negative. So in other words, for the domain of this function, maybe I'll write the word domain here. How would you find the domain of the function inside of the square root? And then the places neighboring that domain will give us the possible candidates for asymptotes. Okay, so you want that to be larger than or equal to 0. If you try to solve this by factoring, this would be like x plus 4 times x plus 5. So this function is going to be changing sign at the numbers minus 4 and minus 5. If you, for example, try to graph this parabola between minus 4 and minus 5, it will be negative. So that means the domain of the function under the square root, the places where this is larger than or equal to 0, is between negative infinity and minus 4, and, or between minus 5 and plus infinity. So as remarked, possible places for vertical asymptotes are the places where the domain kind of stops, places bordering the domain of the function, except that it's actually well defined in this place. We are including the numbers minus 4 and minus 5. So there will not be an infinite limit for the square root function, at least for these numbers. There are no problems there. So we should just say no candidates come from here. It would be a very different issue if the square root was in the denominator. Then it cannot be a 0, so you would not be including these numbers. And then they are potential candidates for asymptotes, but not here. Here only x equals minus 4 is a candidate. So we now just need to understand the limit as x goes to minus 4. Again, it was x squared plus 9x plus 20. Well, plugging in -4 will give you 0 over 0. So you know that something has to be done. You know how to factor. Try to analyze limits from one side here. In a function involving square roots or absolute values, you should probably try both sides separately. Let's see what happens from the right. Sorry, I want to try it from the left first. No, I want to try right. I graphed these. There's a mistake here. Maybe you caught that. Of course, -5 is smaller than -4. Sorry about that. But now, yeah, looking at the domain of this function, we realize that we can only come from the right towards -4. That's why I'm taking a right limit here. But anyway, what is that going to give us? If you're coming towards -4 from the right, the square root in the top, we already know how to factor that. Remember, it was x plus 4 times x plus 5. And we're taking the square root of the whole thing. So we're taking those numbers raised to 1/2. And then divided by what is absolute value of x plus 4. If we already know which side of -4 we are on the right side. So your x is a number that's a little bit larger than -4. If you add 4 to that, it becomes larger than 0. So x plus 4 is positive because you are on the right side of -4. That's what the function becomes if you're coming from the right. And what's happening, you can cancel powers here of the factor x plus 4. In the denominator, it appears entire, and there's only a 1/2 power out in the numerator. So that just leaves a 1/2 power in the denominator. Basically canceled a 1/2 with a 1/2 from here. Okay, cool. What is this? Well, now if you try to plug in, it's not 0 over 0 anymore. It's rather number over 0. Plug in a -4. Upstairs, you have 5 minus 4 is 1. Square root of 1 is 1. Downstairs, x plus 4 is well defined. It's a positive number. And then the square root of that is also a positive number. So it is going to 0, but from positive numbers. So plus infinity because that's positive. But this question was actually just asking about vertical asymptotes. We don't really care to find either plus or minus here. I mean, it's important to find the correct answer, but as soon as we recognize it's a asymptote, it's an infinity value, you know that will be an asymptote. So x equals -4 is a vertical asymptote. The only one, actually. So that's how you would analyze this function. I guess it shows us that the factoring that can happen between numerator and denominator is not always going to be like this with just a polynomial, but you can also have square roots in one of those. A square root will basically give you a power of 1/2. So that can cancel with integer powers and leave some powers behind. That's exactly what happened here. I don't want to move on too much on this, so I will leave these for you guys to just think about, but keep in mind they are more complicated questions than usual. Particularly this one with the cosecant. Just as a reminder, cosecant is 1 over sine. So if you're trying to find all the vertical asymptotes for this function, you have to understand the places where this denominator can be a 0. And there's lots of them, because there's lots of infinitely many actually points where sine is 0. So try to think about this when you're sure that you understand the topic. And also problem 7, which is with a parameter. This is straight from the book, just using different numbers. you have this parameter b in your function, and you're asking what are the values for which you can have a vertical asymptote. You know that just because you have x minus b downstairs does not necessarily mean that the limit as x approaches b will be an infinite limit. In other words, does not mean that this will be a vertical asymptote. In a few cases here, it will not be, so try to find those. That's going to come from the numerator. If you have questions about these, again, just office hours or email. But I'm going to leave this in here now.